Hey everyone, and welcome! Today we're tackling a really interesting LeetCode problem called Meeting Rooms 3. It's a scheduling puzzle that seems simple on the surface, but has some tricky rules that make it a great challenge. We're going to break it down step by step. Okay, here's the core idea. We're given a number of meeting rooms, let's call it N, and a list of meetings. Each meeting has a specific start and end time. The rules for assigning rooms are very strict. First, each meeting must go into the unused room with the lowest number. Second, if all rooms are full when a meeting is supposed to start, it gets delayed. It has to wait until a room becomes free. The delayed meeting keeps its original duration. It just starts later. Our job is to figure out which single room ends up holding the most meetings. If there's a tie, we pick the room with the lower number. Let's walk through this example to really get it. We have two rooms, Room 0 and Room 1. The first meeting starts at time 0. Room 0 is free, so it takes it. It'll be busy until time 10. Next, at time 1, a new meeting arrives. Room 0 is busy, but Room 1 is free, so it goes into Room 1 and will finish at time 5. At time 2, another meeting wants to start, but Room 0 is busy until 10, and Room 1 is busy until 5. Both are occupied. This meeting has to wait. Same thing for the meeting that wants to start at time 3. It also has to wait. Now, let's fast forward. At time 5, Room 1 becomes free. We have two meetings waiting. The rules say to prioritize the one with the earlier original start time. That's the meeting that wanted to start at time 2. So it grabs Room 1. Its original duration was 7-2, so 5 units of time. It starts at time 5 and will end at time 10. Finally, at time 10, both rooms finish their meetings at the same time. Our last waiting meeting can finally go. It uses the room with the lowest number, which is Room 0. Its duration was 1, so it runs from time 10 to 11. Counting it up, Room 0 and Room 1 both held 2 meetings. Since it's a tie, we return the lower room number, which is 0. Okay, how can we translate that logic into a strategy? The first approach is pretty straightforward. First things first, we must process meetings in the order they're supposed to start. So sorting the entire list of meetings by their start time is step 1. Next, we need to keep track of when each room becomes available. A simple array works perfectly for this, where the index is the room number and the value is the time it'll be free. Then, for each meeting, we'll scan this availability array. We're looking for a room that's already free. If we can't find one, we'll have to find the room that will finish its current meeting the soonest. We'll then delay our new meeting, updating its start time to when that room becomes free. Here's the code for that first approach. You can see the two arrays we talked about, one called room availability time and another called meeting count. We sort the meetings first. Then, for each meeting we have this inner loop that goes from Room 0 up to Nivets. This loop is doing two things. It's looking for a room that's already available, and if it can't find one, it's keeping track of which busy room will become free the earliest. If we find an available room, great. We book it and break the loop. If not, after the loop, we use the earliest available room we found, update its count, and add the meeting's duration to its new availability time. It's a direct simulation of the rules. That first approach works, but looping through all n rooms for every single meeting can be slow if we have many rooms. We can do better with a more clever data structure. Priority queues, also known as heaps. The idea is to maintain 2 heaps. The first heap, let's call it available_rooms, will store the room numbers that are currently free. Because it's a min heap, it will always give us the room with the lowest number in a flash. The second heap, we'll call busy_rooms, will store information about the rooms that are in use. We'll store pairs of data, the time a room becomes free, and its number. This heap will be sorted by the end time, so we can instantly find out which busy room is the next one to become available. This is way more efficient than scanning an array every time. And here's the code using priority queues. We start by putting all room numbers from 0 to n-1 into our available rooms heap. For each meeting, we first check the busy rooms heap. We release any rooms whose meetings have already finished by the current meeting's start time, moving them back to the available rooms heap. Then, we check if there are any available rooms. If so, we just pop from the available rooms heap. It automatically gives us the one with the lowest number. If not, it means all rooms are busy. So we pop from the busy rooms heap to get the room that frees up earliest, calculate the delay, and push it back onto the busy heap with its new end time. This is much cleaner and faster because the heaps do the hard work of finding the minimum for us. So let's compare the two. Let's say m is the number of meetings, and n is the number of rooms. For the first approach, Sorting takes big O of m log m. But then, for each of the m meetings, we might have to scan through all n rooms. This gives us a total time of m log m, plus m times n. The space is big O of n for the tracking arrays. The priority queue approach also has the m log m sort. But the key difference is that every heap operation, pushing or popping, takes only log n time. So for each of the m meetings, the work is logarithmic, not linear. This results in a much better total time complexity of big O of m log m plus m log n. The space is still big O of n to store the rooms in the heaps. For large inputs, the priority queue method is clearly the superior choice. So, to wrap it all up, what are the big lessons here? First, for almost any meeting scheduling problem, sorting the events by time is your best first step. Second, we saw a classic optimization pattern. A simple array simulation works, but it has a bottleneck in its linear search. The key takeaway is that priority queues are perfectly designed for problems where you constantly need to find the smallest or next available item. By separating our rooms into two states, available and busy, and managing them with heaps, we arrive at a very efficient solution. I hope this breakdown was helpful and made the problem easier to understand. If it did, a thumbs up is always appreciated. Feel free to subscribe for more deep dives into LeetCode problems. If you have any questions or a different way to solve it, drop a comment below. And hey, if you're feeling extra generous, you can always support the channel through the Boba Fund. Thanks for watching, keep up the great work, and I'll see you in the next one.